So now we know that ions can form very stable compounds of different structures. So how they are bound chemically? What's the nature of formation of 1 mole of solid from gaseous ions is numerically the same as lattice energy. So that's what we name energy of ionic bond. Sodium ion in gas plus chloride ion in gas makes sodium crystalline sodium chloride. It's not a molecule, it's a crystal, and releases 787 kilojoules per 1 mole. Since energy is released, value of this process, of course, should be negative. Smaller ions have greater attractive force, and they have those with higher charges. Energy is electrostatic, so we can apply Coulomb law, stating that energy would be proportional to charge of ion 1, charge of ion 2. These charges are opposite, so total energy would be negative, and divided by distance between this. This constant actually is different from the constant in real Coulomb law. Why? Because we do not have just two particles, sodium and chlorine. We have a lattice, so we have almost infinite number of particles, and we need to add all these. The constant that we should put is named after physicist Madelung, a Madelung constant. Basis for calculation of Madelung constant for rock-salt structure type, showing shells of iron and different distances from central ion that we label 0, is on this animation. Let's look how does it work. So the energy multiplied by some coefficient will be addition of several terms. First, we fix our central ion with 0. Next, we look at its 6 neighbors. First layer, and this is easy to calculate from distance between them. But this is not the end of the story. This is negative, so that's what we want. But then we need to take into account the next layer of ions with the same charge as our 0. So it will be 12 of them, and the distance will be square root of 2 multiplied by this original distance. Of course, this is not the end of the story, because next we'll have another layer of 8 atoms that are square root of 3 distance from our original, and they are opposite charge, so this is negative energy. Next we'll have 6 of ions with positive, and this series will continue way into infinity. That's a difficult mathematical problem. This calculation of such energy is tricky, and numerically it was solved analytically to write an equation, it's impossible. Now, we have Madelung constant determined for common lattice types. For example, for sphalerite and wurtzite, we have almost the same Madelung constant. It's visible that wurtzite is slightly more energetically favorable. Uh, Sodium chloride and cesium chloride have slightly larger Madelung constants with different other structures. We have others and so on and so on. How we can use this to estimate the bonding energy? Born and Landau derived such an equation where n is Avogadro number, A is Madelung constant, Z plus is charge of positive ions, Z minus is charge of negative ions. And these are physical constant. Charge of electron, distance between positive and negative ions, and these are simply 4 pi. Now you need to take into account how many neighbors your ion has, and that's so-called Bohr exponent. So for first row of atoms, when electron configuration of ion is helium-like, you'll have 5. For sodium, magnesium, and oxygen, fluorine, where our basic noble gas ion is neon, you'll have 7. Now next you'll have argon for potassium, calcium, sulfide chloride, and so on. Two last cases are rather exotic. Most commonly you have 9 or something around this. So if you have a large Born exponent, this correction will be smaller. Now, it was detected that Madelung constant is around 0.88 times larger, 0.88 times multiplied by the number of ions in empirical formula. So here you have 2 ions, one zinc and one sulfur, multiplied by 88, you'll have 176. Let's see. Here you'll have 3 ions, so 0.88 again. So practically, maybe we can make another approximation and simply discard Madelung constant at all to make more primitive estimate. This was done some 60 years ago by Kapustinsky, who empirically derived that if you'll put a constant k, a number of ions in empirical formula, of course charge of positive, charge of negative, so say +1, -1, and add radius of cation, radius of anion, and then make a correction term which will be 1 minus, again constant, relatively small number, divided by sum of radius cation plus anion. So this formula will give you a lattice energy with reasonably good approximation. Now, where ionic radii can be taken, again, we have tables or reference books, so we know this number more or less well. If we'll take these numbers of radius and know the composition of compound, Now it's interesting that it's possible to determine ionic radii when lattice energy is known but radius itself is not. This is useful for complex ion like sulfate SO4 2 minus. It's not spherical, but we can talk about radius, effective thermochemical radius of it, or phosphate. Here's the example of NH4 ion. Again, it's not a sphere, but it can be treated as a sphere. So you can do the same calculations and estimate the radius of NH4 ion. Such tables of results that were calculated by this formula. So we have a radii of BF4, carbonate, cyanide, nitrate, hydroxide, sulfate, phosphate, and perchlorate, bromate, iodate. So plenty of different ions.